As Carol pointed out, if you drop out, well, we'll get the recording too, so just hang in there. So Carol's been through all the text box and stuff like that. You should be able to hear me, and I'll just text that in the box. Oh, good, thanks, Alfred. Got the tools wizard there if you can't hear, but you will get a copy of the presentation, so hang in there. This is presented by EIT. Sorry, can't hear. Okay. Mohammed, let me just text in the box. If you can't hear, then your microphone is probably not, your headset. Best to get recording. Yeah, unfortunately, this is always tricky. If your headset's not working properly, then you've got a potential problem. So I'm Dean of Engineering, worked for 30 years in industrial automation, electrical engineering, and of course the topic is about lightning surge protection. And this is the point at which Carol starts recording, and off we go. We had about 250 odd, 220 odd request recordings, and obviously only a few have attended. But we have got a live version of the Electromeet that will make it a bit easier in future, where you don't need to actually install anything. So maybe that'll make it a bit easier in the future. We'll see. For more to attend. This is put together by Cobra Strauss. He's done the presentation here. So I'm just going to take this information over the next few sections. There's two sections here. One is on lightning, which we're doing now, and the second section is on earthing itself. So we'll do the whole thing in about 40 minutes. There's more slides than we can cover in 40 minutes, but you will get the recording and you will have a copy of all the slides. So this is just a sort of idea of the lightning Thunder Day map in Australia, for example. As you can see, the northern part of Australia, there's quite a significant amount of lightning activity, typically 80 days a year, so it's quite significant. It's called the wet season. So quite a lot of activity there. The point we want to make is with lightning, everyone gets a bit traumatized by lightning, but in fact you can probably kill yourself a lot quicker with other forms of exposure. And probably smoking, 10 cigarettes per day. You've got a 1 in 400 chance of dying, all the way through to being struck by lightning, 1 in 2 million chance. So really, lightning's not that probable that you're going to get killed by lightning, although bad stories, people in the Rocky Mountains camping, and the tents hit, and of course you've got 10 kids killed in one shot. So obviously you get some very, very bad stories as well. And it can be quite an emotional topic. But the point made is you've got more chance of being killed with a natural disaster than with lightning. In Australia, which is where I'm based now, I'm based in Perth in Western Australia, 6 to 10 people are killed each year by lightning. So most of the common causes of golf, swimming, sailing, being in large open areas. So it's quite an interesting way. There's a few myths about lightning. We always have our myths, and I'm sure everyone here has certain things. One myth is lightning never strikes twice. Carol, did you believe that?
I'm sure I've heard stories about people who have been hit by lightning more than once. They were probably playing golf and swinging those metal clubs up in the air when they shouldn't have been.
Absolutely right. Thanks very much, Carol, for that witty contribution. Thank you. So as Carol says, lightning does strike twice. It strikes many times. So really, it's a myth. The other thing is, the other myth is that if you're driving a car and you've got rubber tires, you're going to be insulated from lightning. Total, absolute bunkum. Also rubbish. If lightning's traveling for a few kilometers through the air, it doesn't suddenly bypass your car because you've got rubber tires. Other thing is, don't touch someone if they've been hit by lightning. Well, once they've been hit, you can touch them, so no problem at all. Lightning can be prevented. Also, again, not quite true. You can reduce it, but certainly it can be a problem. The other ones are lightning can be predicted. Again, probably not that true either. New high-tech forms of lightning rods can control lightning. Again, not true as well. Bolt from the blue, that's also a misconception, and this is from the National Lightning Safety Council, NSLI. So here's a few examples of localized form of lightning. You can see there's a lot of lightning in one particular area. Here's a bolt from the blue phenomenon. Lightning goes straight out like that. Here's another one, bolt from the blue, straight from the side. Nothing's happening here at all, and all of a sudden you get a lightning strike here, so problem. A few facts about lightning. It's random, unpredictable. No cost-effective practical lightning method can give you 100% protection. So, you've got to obviously follow certain rules, but it's very, very hard. Here you can see, here's a space shuttle, and you can see the lightning bolt should have gone straight that way, but in fact, it didn't. It went on the side. I mean, what on earth would it do that for? So it's gone through the side there. So really, it just wants to show you the unpredictability of lightning. Very important to see that. And that's what you've got to control. So you can have lightning detectors, which detect lightning, but they only give an approximate indication. When is lightning an immediate threat? So there's a few little points here. When is it an immediate threat? Well, typically up to 8 kilometers away. If you hear the flash to bang time 30 seconds or less, which means that lightning speed of light is 300 meters, is obviously light obviously travels at the speed of light, so it's almost instantaneous, but thunder travels at about 330 meters a second. So if you hear something which is 30 seconds from the flash to the bang, your lightning strike is probably 10 kilometers away. So bear that in mind. And that's the time to get under shelter. So if you hear 30-second delay, you've probably got a potential lightning moving in your direction. So probably take shelter. 1 kilometer every 33 seconds, so 330 meters a second. Safe shelters are fully metal enclosed vehicles, large metal sheds. Unsafe shelters, very important, trees, target number 1 for lightning, vehicles with open sides, tents, another big target, and bear in mind that the surface arc where the lightning strike is, which I'll show you now, here's the lightning hit there, and of course the surface arc goes quite far. So the lightning goes from that strike quite far out. So just bear in mind it's quite a issue. The protection principles, let's have a quick look at that. Is everyone on the same page as me? If you're on the same page, if you can please put up your smiley face like that. Just put a smiley face or something up there to show that you're happy. Carol, if you could do that. Thank you very much, Carol. Just put a smiley face. Thank you very much, Sianda. Nadim. And anyone else listening? Mohammed obviously can't hear. And Alfred can't hear either. And Juturish can hear as well. Okay. Carol, did I tell you the joke about the chauffeur? I think I must have. At this point, I need to.
I think you told us in the last session, right at the very end of the last live webcast.
Yeah, I'm getting old, Carol. Thank you. Thank you for minimizing my embarrassment. Okay, I was going to tell you a joke, but as Carol's pointed out, I've told it 3 or 4 times already. And in fact, if my boy hears it one more time, he gets a bit agitated. My 15-year-old boy. Anyway, protection principles we're looking at are air terminal, down conductors, earthing and bonding, surge protection, safety procedures. So I just want to briefly look at these. Here's a typical air terminal on top of a structure. Not much protection there at all, unfortunately, because the lightning could hit there, so not much help. But the client has paid quite a lot of money for that. Here's another example. Here's protection terminals there and there. Again, unlikely to be much protection. Here, again, you've got, if you look carefully at this diagram here, you've also got protection, and again, not much protection at all. I can go around there. Here's a good example of incorrect earthing practice. Can anyone tell me what the problem is here? Now, basically, the idea is that the lightning, this is for a pole, the lightning should go down here and then go down to Earth. Can anyone tell me what the problem with this design is? You can text it in your boxes if you want. Text in box. You can tell me what the problem here is. Yes, coil wire. Thank you very much, Sianda. And why is that a problem? Yeah, that's not bad. You're pretty close, Sianda. As Sianda says, there's an actual higher level of impedance here. So this actually forms a coil. And when you get your high frequency lightning strike come down here, this actually is extremely high Z or Z or impedance. Yeah, so Sianda was pretty close to it. So this has been done by the tradesman or electrician to try and sort of wind up the wires so you can actually use it for future applications. Perhaps he wants to stretch it a bit further, but of course not a good idea at all because it just creates that thing. Now the other thing you can use is a surge arrestor, which actually picks up the surge going down the wire and also protects. But the problem with the surge arrestor, it needs to be earthed. And of course, it's not earthed correctly here at all. There's an earth cable there. But this here hasn't been earthed. Instructions say, please earth the surge arrestor. Here's another example, surge arrestor, which is supposed to take your lightning or your surge and take it down to earth, but nothing done. So again, completely useless. Here's a little example, a little subtle example here, where there's a whole lot of surge arrestors here in this little box here for a lot of wiring. The problem is the wiring for the surge arrestors on both incoming and outgoing are all mixed up. So again, you introduce surges back into wiring. So surge arrestor, again, absolutely useless. So these are little issues we need to watch out for. Here's another example here. All the wires very neatly put together, but absolutely useless. So watch out for these. These are real examples. Here's an example of a plane hit by lightning. And obviously the idea with lightning is that the plane should be immune to any strikes. And as you all know, sitting on a plane, always get a bit jumpy when you see a strike. Always get very, very jumpy, but you should be fine. And I might ask, Carol, is my voice okay? All okay? Can you hear me okay?
Yes, can hear you loud and clear, Steve. Keep going.
Thanks very much, Carol. Now we move on to the next stage, is we want to talk about actual earthing, power system earthing. So I've spoken about lightning. Let's put that to bed. Now everyone here is going to be confronted with a few questions, and of course, those questions, if they're answered correctly, you will get a little prize of an e-book, which is worth $50 to $100, maybe more, or 60 or 70 pounds. Although the way the pound is going downwards, it's probably worth 1,000 pounds by the end of the year. But anyway, let's not joke about currencies because they are a little bit painful. So we've got a few quiz questions here in the next section, a few prizes, and Carol will take open a few questions there. So I just want to really talk about earthing in a little bit more comprehensive depth. Again, I must say I'm very grateful to my colleague from a firm of consultants, Rodney Urban, who's allowed us to reproduce these slides from some work he's done with earthing, which he's charged his clients thousands of dollars to do. So I just want to briefly talk about earthing. As I say, I don't want to waste too much of your time. Earthing requires a specific design process. You need to accommodate uncertainty in inputs. In other words, you don't always get precise information. You need to look at the variations in soil resistivity. Can anyone tell me what soil resistivity is? What is soil resistivity? Resistivity. You can type it in your box or talk to me. You can talk. Has anyone got a microphone? Okay, thanks, Alfred. Yeah, it's the resistance of the Earth. Okay, someone's got a microphone. That's fine. It's resistance of the Earth, and it's actually, there's a formula to calculate it, which I'm not going to worry about here, but it basically is a property of the Earth showing the degree of resistance to current going through it. And it does vary from site to site. So, for example, if you've got a site which is very dry, like Libya, you guys, we've got someone from Libya here, Nadim, I think. Obviously, it's sometimes very difficult if it's dry, there's no water, whereas if you've got, yeah, exactly. Thanks very much, Mohammed. And Mohammed, is your headset working? Can you hear us? You obviously can. That's good to hear. Delighted. I thought you were just looking at the slides. But Mohammed, thank you very much. Delighted to hear that you're hearing us. So Nadim, as Nadim remarks, sand, oh, that's good. Thanks, Mohammed. That's fantastic. If you're in the desert, your sand can create a very high level of resistivity, so it can be a lot more challenging. If you're in a very clayey soil, lots of clay and water in the soil, you'll find the resistivity moves down. And also, the other little challenge you have, which I'll show you this with the example here, the resistivity can change throughout the year. So basically, you have a dry season and a wet season. And the example I'm going to give you here is Sydney in Australia. And Sydney has enormous wet parts of the year, and then it has very dry parts of the year. And the resistivity changes through the year. So when you do the design, which I'm going to go through now, you actually have to watch out for the changes in the resistivity of the soil over the year. So you've got to look at the worst case scenario. So resistivity is a key factor determining resistance of the electrode. You get a wide variation, and it's largely, actually, funny enough, it's a chemical reaction. Moisture, minerals, dissolve salts. And the resistivity can change about 20% with more moisture content. So if you've got lots of moisture, you're laughing. But bear in mind, when you do your resistivity calculations, which I'm going to go through now, you need to make sure that you look at the worst case scenario, so the driest part of the year, for example. Don't look at the best case scenario, otherwise you won't have very happy clients. So resistance of an electrode is actually the resistance for the metal electrode, and the contact resistance and the resistance of the soil. So basically, when you put an electrode into the soil, that's the soil there. I could just put a little, that's your soil. It actually depends on the resistance of the electrode, the contact resistance around it, and obviously the resistance of the soil. If you increase the diameter of the rod, so you make it a bit fatter, you don't actually reduce resistance much. If you increase the length of the rod, you reduce the resistance quite significantly to 40%. Obviously, if you've got rock here, it's a lot of a challenge to get it in. The other way to reduce resistance is to put in multiple parallel electrodes. So here's a typical example. Resistivity is in ohm centimeters or ohm meters, but ohm centimeters we often use. And you can find that your resistance, you calculate with rho ohm centimeters divided by 298 for a 3-meter rod by 60-millimeter diameter. So it's quite a thick rod. So it just gives you a sort of quick example. The other thing about current loading capacity is Earth can dissipate high currents for short durations, but you've got to watch out for smoking. If you've got a lot of current going through that Earth rod, you may find you've got problems. And this is the calculation here for the maximum current in amp meters. Question for you guys. First question, there's 2 or 3 of these. Why is crushed rock spread all over the surface of soil within the substation grid area? When you look at your substation grid, from an earthing point of view, you'll see a lot of crushed rock spread out there. Can anyone tell me why? Question to you guys. Giving you 30 seconds. You can text it in your box. Just text it in the box here. Text in box. First question. Yeah. Thank you very much, Sianda. You're actually a genius. In fact, you should be with your microphone presenting. That's quite true. Thank you very much. Sianda, can you just tell us quickly, because some of the others may not be familiar, what is step potential? Yeah, poor conductivity. Thank you, Alfred. Yeah. You guys are quite sharp. Okay. Without wanting to sound patronizing, we've got two very sharp people here. Sianda, you get the ebook of your choice, and Carol will take your details and give you that there. So, Carol, if you can grab Sianda's details, you can take an ebook worth $120 from our library. And to answer the question, the crushed rock provides a high resistance surface to reduce the hazard from a step potential. I think you must have read those slides, Sianda. How did you know that so quickly? Sianda is quite right. Step potential to persons within this area. So step potential is basically the potential across your steps, across your feet. There's two types of potential, step and touch potential. So we're worried about step potential as substation, and you've got granite rock, which when even wet has a very high insulation resistance of 4.5 times 10 to the 5 centimeters. So even when wet, it's very high resistance, which means that if you touch something, you're still okay in that substation. So that's why you have rock there. Okay, now just to look at ways to work out your soil resistivity, you obviously want to say, well, what's the deal with the soil resistivity? There's two methods. One is the Wenner method. As you can see in this diagram here, it's a little bit difficult to see, but you can see there, basically what you've got is you inject the current over here, and you measure the potential. And of course, good old R equals V over I, which we learned from when we were 4 years old. You can then work out the resistance between there, and you can then work out your resistivity. The other one is the Schlumberger method, which is a little bit simpler. You can see the formulas there, but I'm not going to worry too much about this. But basically here, if I just go back, the deal there is that you'll see there that the distance between the electrodes A is the same as A. Unfortunately, not to scale. Naughty Rodney. Well, I can probably could have redrawn it myself. But basically, it means that your calculation is a lot easier. The resistivity is 2 pi r, so it's very easy to calculate resistivity of the soil. 2 pi times the resistance that you measure by calculating the voltage drop over the current. So very easy to work out. But this one is where you've got a variable distance here. Sometimes you can't get your probes set up very easily, so that's called the Schlumberger method. Again, very easy to measure the soil resistivity. Biggest constraints in measuring, of course, are physical site constraints, metal surfaces and structures, limited site access. Sometimes people won't give you access to their properties to work it out. And this particular example is on rail corridors. There are significant constraints with trains. Trying to measure with a train running past you is always difficult. And sometimes you can't get into measure, and you're trying to put a substation down for their railway line. Input data you need is dig before you dig, dial before you dig. So first of all, you find out there's nothing below the surface of the ground when you're trying to do your soil resistivity calculation. Any buried services like water pipes and electrical reticulation, geotechnical data, meteorological data is like what is rainfall like and that sort of thing. So I just want to briefly run through 3 case studies very quickly. Before I do that, what is transferred earth potential and how does one deal with it at a substation? This is the next question for you guys. What is a transferred earth potential and how does one deal with it at a substation? So you've got substations and you want to work it out. Any suggestions there? Any ideas? I know you all think, and Carol's probably thought, oh, he's probably dropped out of the internet. Do you think I disappeared, Carol? Okay, Alfred's made a good suggestion there, but and that's probably one way. As Alfred said, that's a very practical way. Maybe a better solution, actually. Carol's always worried that I've dropped out, and at home when I present, I sometimes find my wireless connection is a little bit traumatic, and then it drops out, and then I'm gone. But I'm in the office supposedly with a high-speed connection, although sometimes one wonders. Okay, little thing there, suggestion there. Earth potential rise of the substation can be about 5 kilovolts, which can be transferred to a non-fault location by a ground conductor, metal pipe rail. Probably the best thing is to bond together the ground mats and use isolation transformers. So earth potential rise due to some electrical fault. So we're suggesting bond together the ground mats and use isolation transformers, 2 suggestions. Okay, but Alfred's probably got a good suggestion as well. But sorry, as they say in the classics, no cigar. That was the answer I was after. Case study number 1, courtesy of Rodney again. Project description, 5 kilometers duplicated track, new traction substation, and we've got a new passenger station with 11 kV supply, 11,000 volts, and we want to look at some solutions to earthing. So what we're trying to show you here is you've got the rail going along, and you've got this area here, and we want to work out the actual resistivity here, so we can actually work out our thing. So we take 2 traverses perpendicular to each other, and we then work out resistivity that way. And difficult to see on this diagram here, but you can see that there's a resistivity which changes like this. I'm sketching like that. And the idea is that these are the 2 different graphs, and the idea is that we look at these numbers to try and work out the best figure. So here's a typical resistivity. As you can see here, as you go further apart, you actually get more insight into something further down. So basically what we're saying here is the thickness. You can see here at the top, you've got 105 ohm meters. As you go down 66 meters at the bottom, you've actually go to infinity. So it actually, as you go deeper, your resistivity doesn't change too much for this particular one here. So you can see that you've got different values here, and you need to sort of interpret these numbers into something intelligent. So what we're trying to prove from case study 1 is that there's a very low resistivity clay aquifer. Aquifer is sort of a zone below the surface of the ground which has got water in it. And the geotechnical data actually and the resistivity actually tell you what's going on. So basically, the geotechnical tells you the different types of rock you've got below the surface, or clay or rock or sand that you've got below the surface, and the different layers you can get from the geotechnical, and you can then correlate them to the resistivity values which you then are picking up. So it's great to get to doing. There's quite a lot of soil drying here in the dry season of Sydney, and you'll see the resistivity actually jumps quite dramatically over the year. So the point to make is you've got to watch out for changes in the seasons with different weather. Next question for you guys. I think this is the second last question. Why is galvanic corrosion a problem for electrodes, and how does one deal with it? Any suggestions? I won't disappear this time, Carol. I'll just wait quietly for 30 yeah, cathodic protection is probably the answer. Yep, thanks Nadeem, you can get a free book. What I was hoping for is a little bit more detail answer, but cathodic protection is right. I can't dispute that. So galvanic corrosion is caused by electrically connected to similar metals. So you, for example, copper used in the rods can seriously damage underground structures, such as iron or steel that are electrically connected. Thanks very much, Alfred. The rod and the earth conductor, yes. Yeah, we don't want to insulate it. What we're going to do is you could use a different metal to copper, something closer to iron. So, for example, if you got your copper electrode connected to an iron structure, you'll find your iron will be destroyed. So basically what you do is use something different to copper, something closer to iron, so less likely to create a problem. And it's along the idea of cathodic protection where you have sacrificial anodes. So the last thing you want to do is put your earthing system in and damage the structures that it's supposed to be protecting from a thing because of electrical or chemical action. So second one is a case study here, signaling upgrade project. Again, we've got geotechnical data and service layout data, and the idea here is, I think you can see here on this diagram, here's the railway line, and we're looking for a, we're looking to put in an earth setup here. So again, difficult to work out here, but the point I want to make is you can get a diagram here of resistivity over distance, depth, and you can then make out some ideas here. So basically what we've got here with this section here, I'm just circling it, you can see your top layer of earth, 98 meters with a thickness of 1.11 meter. As you go further down, you can see there's a bit of the resistivity actually drops in the middle. Probably it's got liquid or clay. And then right down near the bottom middle to 10 meters, you've got it suddenly jumps again, probably rock. And then as you go further down, it drops to 58 meters, and that's thickness going as deep as you can. So the idea with case study 2 is use of the Wenner method, which I've mentioned earlier on, with probe spacing of 40 meters, 18-meter vertical electrode to penetrate the bottom layer, because there's some insulation from the top layer, and look at the depth and resistivity there. So the idea is plot data at time of measurement, identify critical design parameters. So all we're trying to do is look carefully at what you're doing. Case study 3 is a bit of a problem here. We want to put a substation here, and we do the traverse, the measurement, along this black line here. You can see there's a road there, and we're going to put the substation there. And obviously we want to do the measurement at this point here, but we need a fairly lengthy distance. So here's an example here of the electrode spacing. Here's the resistivity up that axis there, and the inter-electrode space, as you can see, it gets wider and wider. And as you can see, as it goes further, wider and wider, your resistivity actually drops quite a bit. That's for Traverse 1. The other Traverse 2, we normally do the traverses perpendicular to each other. And here you can see it actually drops and then sort of stays fairly low. So here's case study 3. You've got a water pipeline parallel to the main test, and that's interfered with the test data for the middle thing. So when you're doing your earthing measurements or your resistivity measurements, you've got to be careful that you're not close to any water pipelines which could impact on your measurement. And you will find today that water pipelines are not such a big issue that they were, say, 20 or 30 years ago. And why would that be? It's because we don't use steel pipes anymore. We use good old PVC. So that doesn't have a problem. So just to show you again with this diagram here, oh, sorry, jumping around. Here we've got the soil resistivity again, upper, middle, underlying for Traverse 1. And you'll see as you go down, your resistivity drops. And Traverse 2 sort of drops and then it goes up again here. So not quite conclusive, but it should give you some idea. So variations in soil resistivity are source of uncertainty. You've got to look at the cost-effective solution, look at your site constraints, make use of other data such as your geotechnical. And the other very important issue, which Rodney made a big point of, try and plot your measurements during the actual resistivity measurement process. Do not wait 3 hours till you go back to the office. Otherwise, you may see there's some kink in the information or the data which you should have picked up then. Because to go all the way back to the site, maybe 3 or 4 hours, maybe a day's travel or something. So try and do your measurements then and there. Okay, that's about it from me. I've gone through 2 issues in a rather lengthy period of time. Thank you, Suganthan, for joining us. We've gone through lightning and we looked at earthing. So we've compressed a lot of information into 40 minutes. I normally have a more interactive approach, but you guys have been very good. So thank you very, very much for your wonderful participation, for coming along. This will be recorded so you can get a copy of it, and really appreciate it. So thank you, Carol, for hosting it. Carol's in London, I'm in Perth in Western Australia, and you guys are in Africa and Asia perhaps. And the other 200 that requested the slides, we will get a copy too. So thank you very, very much, Alfred, Carol, Mohammed, Nadeem, and Suganthan. Suganthan, sorry, you only joined at the bit. You're in South Africa, that's right. Siada. Thank you very much to all of you for joining. Over to you.